You ever wonder what's really hiding inside the math you learned way back in school? Well, it turns out some of the absolute simplest expressions can be gateways to some incredibly deep and surprising ideas. Today, we're going to go on a little journey that kicks off with a basic factoring problem you've probably seen before, and it's going to end with a fundamental truth about prime numbers. All right, let's dive right in. So, here's our roadmap for today. We're going to start by factoring something that should look pretty familiar. Then we'll meet this family of, special polynomials and discover this really beautiful, simple pattern they all seem to follow. But then, and this is the fun part, things get really interesting when that pattern just suddenly breaks. And to wrap it all up, we'll see how this whole story connects back to the infinite world of prime numbers. All right, part one. Let's start with something we all know, factoring. You probably remember it from algebra class, right? It's all about breaking down a math expression into its simplest building blocks. It's kind of like finding the prime factors of a number, but for polynomials. Our entire story today really revolves around this one simple question. This expression right here, x to the power of n minus 1. I mean, it looks so straightforward, doesn't it? But as we're about to see, it is packed with hidden structure. For pretty much any whole number n you can think of, you can factor this thing. You can break it apart into smaller pieces. So, for example, let's just take n equals 3. X cubed minus 1. That factors into two parts. You've got x minus 1 and x squared plus x plus 1. Now, that first part, x minus 1, that's simple enough. But the second part, that's where things get interesting. That polynomial, x squared plus x plus 1, you can't factor it any further using just plain old integers. We call that an irreducible polynomial. You can think of it like a prime number, but in the world of polynomials. It's a fundamental building block, and it's these special, irreducible pieces that we're really after. So in that last example, the new, interesting piece that showed up for n equals 3 was that x squared plus x plus 1. Well, it turns out that for every value of n, there's a unique, irreducible factor just like it that appears for the very first time. And these are the stars of our show. And of course, they have a name. They're called cyclotomic polynomials. We write them with the Greek letter phi, like this, phi n of x. Now, I know the definition up here sounds a little technical, but the core idea is actually really simple. The nth cyclotomic polynomial is just the brand new irreducible factor you get when you look at x to the n minus 1, that you couldn't find in any of the earlier versions. It's the primitive, unique piece that belongs only to that specific n. So how do we actually find them? Well, it turns out they all build on each other in this really neat way. The expression x to the n minus 1 is actually the product of all the cyclotomic polynomials for the divisors of n. That gives us a really clean way to calculate them. For example, to find the sixth one, phi 6 of x, you just take x to the 6 minus 1, and you divide out the polynomials for the other divisors of 6, which, are 1, 2, and 3. Okay, now that we know what these things are, let's actually look at the first few of them. Let's see if we can spot a pattern. This is where our story gets really, really good. All right, check it out. Here are the first 10. We've got phi 1 of x, phi 2 of x, all the way down. And as we go down the list, you can see they get longer, a little more complicated. But I want you to take a really close look at the numbers in front of the x terms, the coefficients. Does anything stand out to you? Did you see it? For every single one of these, no matter how messy the polynomial looks, every single coefficient is either a 1, a -1, or a 0. It's this beautifully simple, super elegant pattern, and for a long, long time, mathematicians actually thought this might just be a universal rule for all of them. And right here, this is the moment of discovery. That simple, elegant little world we were just looking at, well, it's about to get a whole lot more complicated. You see, this pattern isn't just some fluke of the first 10 examples. It keeps going. It holds for n equals 11, for n equals 50, for n equals 100. In fact, this simple rule holds all the way up to n equals 104. I mean, for over 100 straight cases, the rule is perfect. The only coefficients you ever see are 1, -1, or 0. It absolutely feels like a fundamental law of the universe. But what happens at the very next step? What happens at n equals 105? So why 105? Why is that the magic number? Well, it's not random at all. It has a very special property. It is the very first number that is the product of 3 different odd prime numbers. You've got 3 times 5 times 7. And it's this unique structure. That's what triggers the big surprise. And here it is. the 105th cyclotomic polynomial. Just look right there, minus 2 times x to the 41st. For the very first time in 105 steps, a coefficient that isn't 1, -1, or 0 just pops up, a -2. It's this shocking discovery that just completely shatters the simple pattern we thought was a rule. It's a brilliant reminder that in math, patterns can be really deceiving, and it's the exceptions. That's where the most interesting stories are hiding. So at this point, you might be thinking, okay, that's a cool little pattern-breaking curiosity, but what's the point? Why should I care? Well, these polynomials, they aren't just a mathematical party trick. They're actually a surprisingly powerful tool for proving some of the most fundamental ideas in all of number theory. Yeah, one of their most elegant applications is in proving that there are infinitely many prime numbers that follow a specific pattern. For example, proving there's an infinite number of primes that are always one more than a multiple of some number n. This is a really famous result, a special case of what's known as Dirichlet's theorem. And the proof itself is just this clever, beautiful piece of logic. It's a classic proof by contradiction. First, you start by making a bold assumption. You say, okay, what if there's not an infinite number of these primes? What if I could list every single one of them out? So you take that supposedly complete list and you use it to build this new enormous number. And here's the magic part. You plug that giant number into our cyclotomic polynomial, phi n. It turns out that any prime number that divides that result has to be a new prime of the exact same type, one that wasn't on your original list. And boom, that's the contradiction. Your complete list wasn't so complete after all. This forces you to admit your first assumption was wrong. The list must go on forever. The cyclotomic polynomial is the engine that makes this entire beautiful proof run. So let's just wrap this all up. We started with this super simple expression, x to the n-1, and we found it was packed with these unique factors called cyclotomic polynomials. We saw this amazing simple pattern in their coefficients that held true for over 100 steps, only to be totally broken at n equals 105. And finally, we saw that these abstract ideas aren't just weird curiosities. They're actually powerful enough to prove deep truths about the infinite nature of prime numbers. It really just leaves you with this fascinating question to chew on, right? We started with something that looked totally simple. We found a pattern, we saw it break in a spectacular way, and then discovered a much deeper truth because of it. It just makes me wonder, how many other simple patterns that we just take for granted in math are out there, just waiting to reveal a hidden universe of unexpected complexity?